Have you ever had a thought that just stopped you in your tracks? A question so simple, it seems stupid, but the more you think about it, the more your brain starts to melt. Like, can you ever really touch anything? If atoms never truly make contact, are you just floating a tiny, tiny distance above your chair right now? The ancient Greeks loved these kinds of questions. They weren't just being difficult. They were testing the limits of logic itself. They understood that a good paradox isn't just a clever riddle. It's a crack in our understanding of reality. And prying at that crack is how you learn something new. These aren't just dusty old puzzles. They are the intellectual ancestors of everything from calculus to computer science to quantum mechanics. They force us to ask whether motion is real, whether identity is an illusion, and whether truth itself can be a lie. They show us that the simplest questions are often the most profound. And thousands of years later, we're still wrestling with the answers. What if everything you think is solid and real is just an illusion created by your mind to make sense of an infinitely complex world? What if the most basic rules of logic can be tied into a knot from which they can never escape? Number 7. What makes something itself? Imagine a hero. His name is Theseus. He sailed to Crete, killed the Minotaur, and saved a group of young Athenians. His victory was so legendary that the people of Athens decided to preserve his ship as a memorial. They kept it in the harbor for hundreds of years. But time is cruel, even to the ships of heroes. A wooden plank would rot, and the shipwrights would replace it with a new identical plank. Then another would rot, and they'd replace that one too. This went on for centuries. After 1,000 years, not a single one of the original wooden planks remained. Every piece of the ship had been replaced. So, here's the question. Is this still the Ship of Theseus? This is the famous Ship of Theseus Paradox, and it's one of the oldest and stickiest puzzles in Western philosophy. The Greek historian Plutarch is the one who wrote it down for us around the end of the 1st century AD in his work, Life of Theseus. He presents it just like that. A simple, practical problem that spirals into a total mind-bender. Most people would probably say, yes, it's still the ship. It's in the same spot. It has the same design. It serves the same function as a memorial. It has a continuous history. The changes were gradual. But if you say yes, you're implying that an object can survive the complete replacement of all its component parts. This feels a little strange. If you replace every single part of your car, engine, chassis, wheels, everything, do you have the same car or just a new car of the same model? The problem gets worse. The 17th century English philosopher Thomas Hobbes added a brilliant twist. What if, he asked, you had collected all the old original planks as they were removed? And what if, in a warehouse next to the harbor, you used those original planks to reassemble the ship exactly as it was? Now you have two ships. You have the repaired ship in the harbor, and you have the reassembled ship in the warehouse. Which one is the real Ship of Theseus? You know, if you say the one in the harbor is the real one, you have to explain why, even though the one in the warehouse is made of all the actual original matter. If you say the one in the warehouse is the real one, you're saying the ship was sitting in a pile of planks for a while, and the thing in the harbor that everyone called the Ship of Theseus was actually an imposter all along. You can see the problem. There's no easy answer. This isn't just a fun puzzle. It's a deep question about the nature of identity over time, and it applies to almost everything, especially us. Your body is constantly replacing itself. The atoms that make you up today are not the same atoms that made you up 7 years ago. The number often cited is that 98% of the atoms in your body are replaced each year. While the exact timeline for different tissues varies wildly, skin cells replace quickly, some neurons last a lifetime, the principle is the same. You are in a constant state of material flux. So are you the same person you were as a child? You feel like you are. You have memories, a personality, a continuous stream of consciousness. But physically, you are almost a completely different collection of matter. This suggests that your identity, your you-ness, isn't tied to your physical stuff. So what is it tied to? Is it the pattern, the information, the memories? Modern science and technology make this even more complicated. Think about a corporation. Apple Inc. today has almost no employees, buildings, or materials in common with the Apple Inc. of 1980. Yet, for legal and economic purposes, it is considered the same entity. Its identity is based on its structure, its name, its legal paperwork, a continuous history. It seems identity can be a practical label we apply, not some deep metaphysical property. Philosophers like Derek Parfit, in his 1984 book Reasons and Persons, argued that maybe our idea of a single continuous self is the problem. Maybe there isn't a simple yes or no answer. He suggested we should think in terms of psychological continuity. You are linked to your past self by overlapping chains of memory and personality. The link is strong between you today and you yesterday, but it's much weaker between you today and you as a 5-year-old. Maybe strict identity is an illusion, and what we really have is just degrees of relatedness. The paradox forces us to confront what we mean by sameness. There's qualitative identity, two things being exactly alike, like two new iPhones from the same factory, and numerical identity, something being one and the same thing over time. The Ship of Theseus paradox is about numerical identity, and we still don't have a consensus on what it takes for something to maintain it. We are nowhere near solving this. The more you think, the stranger it gets. What if you slowly replaced a person's neurons one by one with perfectly functioning artificial neurons that replicated the original's function exactly? At what point, if any, would the person cease to be them? Would they even notice? If we could create a perfect atom-for-atom copy of you, including all your memories and thoughts, which one is the real you? Does the original have a special claim to your identity just because it was first? Or is identity just a story we tell, a convenient fiction that helps us organize the world with no real basis in reality itself? Number 6, where do you draw the line? Imagine a heap of sand. It has, say, 1,000,000 grains of sand in it. That's definitely a heap. Now, you reach down and remove one single grain of sand. Is it still a heap? Of course it is. No one would argue that removing one grain changes a heap into a non-heap. Now you remove another grain, and another. And another. Each time you remove a single grain, you don't change the heap into a non-heap. But you keep doing this, eventually you'll be left with just 3 grains of sand. Is that a heap? Probably not. 2 grains? No. 1 grain? Definitely not a heap. So here's the problem. At some point in this process, the heap must have stopped being a heap. But when? Can you point to the exact grain of sand whose removal transformed the heap into a non-heap? This is the Sorites Paradox, and it's another one attributed to the ancient Greeks, likely Eubulides of Miletus, a contemporary of Aristotle. Sorites comes from the Greek word soros, which means heap. It's a paradox about vagueness. Our world is full of vague concepts: heap, tall, bald, old, rich. We use these words all the time, and they work perfectly well. You know, a tall person when you see one, you know, a bald person when you see one. If you accept both of those premises, then you can repeat the second premise over and over again until you are logically forced to conclude that 1 grain of sand is also a heap, which is clearly false. So something has gone wrong with our logic. This isn't just about sand. Think about a man with a full head of hair. He is not bald. Now he loses 1 hair. Is he bald? No. What about another hair? Still no. But if he keeps losing hairs one by one, he will eventually be bald. But there is no specific hair that made the difference. The same applies to colors. Imagine a spectrum from red to orange. You have a patch of color that is clearly red. You change the wavelength by an infinitesimal amount towards orange. It's still red. You do it again, still red. But if you keep doing this, you will eventually have a color that is clearly orange. Where did it stop being red? There is no line. For centuries, philosophers tried to solve this by saying that there must be a sharp line. We just don't know where it is. This view is called epistemicism. Timothy Williamson, a modern philosopher at Oxford, is a major proponent. He argues that for any vague term like heap, there is a fact of the matter. There is a precise number of grains of sand that marks the cutoff between a heap and a non-heap. We can never know this number, but it exists. To many, this sounds absurd. It seems crazy to think there's a secret, unknowable rule of the universe that says 1,432 grains of sand is a non-heap, but 1,433 grains is a heap. Another approach is to change the logic we use. Classical logic is built on a binary system. Every statement is either true or false. There's no in-between. The statement, "This collection of sand is a heap," must be either 100% true or 100% false. But maybe that's the problem. In the 1960s, a computer scientist named Lotfi developed a new system called fuzzy logic. Fuzzy logic allows for degrees of truth. A statement can be 90% true or 50% true or 10% true. In the system, a collection of 1,000,000 grains is 100% a heap truth value of 1. A collection of 1 grain is 0% a heap truth value of 0. A collection in the middle, say 5,000 grains, might be 60% a heap truth value of 0.6. This seems to match our intuition much better. Fuzzy logic is now used in all sorts of real-world applications, from the automatic focus in your camera to the anti-lock brakes in your car and the temperature control in your air conditioner. It's a practical solution born from a 2,400-year-old philosophical headache. The Sorites Paradox is still a massive issue in philosophy of language and law. Think about legal definitions. At what point does a company become a monopoly? When does a person become legally old? When does a fetus become a person with rights? These are not trivial questions. They have huge real-world consequences, and they all run into the problem of vagueness. The paradox shows us that our language, which feels so precise, is built on a foundation of shifting sand. Is vagueness a feature of the world itself, or just a limitation of our language and minds? If we had infinitely precise language, would the paradox disappear, or would reality itself still be fuzzy at the edges? If there really is a sharp line between a heap and a non-heap, as some philosophers argue, what kind of physical law determines it? And if morality contains vague concepts like a good person, does that mean there can be no objective truth about whether someone is good or not? Number 5 is goodness arbitrary. Let's picture Socrates in ancient Athens. He's on his way to the courthouse to face his own trial for corrupting the youth. On the steps, he runs into a young man named Euthyphro. Euthyphro is there for a very unusual reason. He's prosecuting his own father for murder. A servant had killed a slave, and Euthyphro's father had tied the servant up and left him in a ditch while he went to ask the authorities what to do. The servant died of exposure before his father got back. Euthyphro is supremely confident that prosecuting his father is the right and holy thing to do. Socrates, as always, is intrigued. He sees an opportunity. He asks Euthyphro, a supposed expert on religious matters, to teach him. What, Socrates asks, is piety? What makes a good action good? This setup, from Plato's dialogue Euthyphro, leads to one of the most powerful and enduring questions in ethics and theology. Euthyphro first says that what is holy is what is dear to the gods, but Socrates points out that the Greek gods were always fighting. What's dear to Zeus might be hateful to Hera, so the same action could be both holy and unholy. Euthyphro refines his answer. Holiness, he says, is what all the gods love. Socrates then corners him with a killer question. The one that we still wrestle with today is something pious because the gods love it, or do the gods love it because it is pious? This is the Euthyphro dilemma. It presents two options, and both seem to have massive problems. Let's break it down. Option 1. Something is good because God commands it. This is known as divine command theory. In this view, morality is based entirely on the will of a divine being. If God says do not murder, then murder is wrong. If God had said murder is good, then murder would be good. The good is whatever God happens to choose. The problem here is that it seems to make morality completely arbitrary. God could have commanded cruelty, theft, and torture, and those things would have been morally right. It empties the word good of any real meaning. To say God is good would just mean God does what God wants, which is a meaningless statement. It doesn't seem to offer a solid foundation for morality, just a foundation based on raw power. Option 2, God commands something because it is good. This option sounds better at first. It means there is a standard of goodness that exists independently of God. Goodness is a real thing in the universe, and God, being perfectly wise and good, recognizes this standard and commands us to follow it. The problem with this horn of the dilemma is that it seems to compromise God's omnipotence and sovereignty. If there is a moral law that exists outside of God, then God is not the ultimate source of everything. And God becomes more like a cosmic moral traffic cop, directing us according to a set of rules that God did not create. Morality is no longer dependent on God. In fact, God becomes dependent on morality. This raises the question, if goodness exists as an independent standard, why do we need God in the moral equation at all? We could just study this standard of goodness directly. The dilemma has been a thorn in the side of theologians and philosophers for millennia. Thinkers like Thomas Aquinas tried to find a way out by arguing that it's a false dilemma. He suggested that God's nature is the standard of goodness. Goodness isn't something external to God, nor is it an arbitrary whim. It's a reflection of God's own unchanging, perfectly rational and benevolent character. So, God doesn't consult an external rulebook, and God can't just decide that cruelty is good because that would violate God's very nature. This is a clever answer, but some argue it just pushes the problem back a step. Is God's nature good because it's God's nature? Or is there a reason why that specific nature is the good one? The Euthyphro dilemma remains incredibly relevant. It's at the heart of debates between religious and secular ethics. It forces us to ask where morality comes from. Is it a set of commands from a higher power? Is it a set of rational principles we can discover through reason, like the laws of mathematics? Is it an evolutionary adaptation that helped our ancestors cooperate and survive? Or is it just a collection of cultural preferences and personal feelings? The question Socrates posed on the courthouse steps is still waiting for a satisfying answer. If morality is not based on a divine command, where does its authority come from? Why should anyone care about being good if it's not backed by ultimate power? Could a being be considered all-powerful if it was bound by an external moral law? It did not create. And if we accept that God's nature is the standard of goodness, what happens if different religions present us with gods of fundamentally different natures and commands? How do we choose which one is truly good? Number 4, can a sentence be both true and false? This statement is false. Take a good look at that sentence. It seems simple enough, but it's a logical bomb. Let's try to figure out if it's true or false. First, let's assume the statement is true. If it's true, then what it says must be correct, and it says that it is false. So, if it's true, it must be false. That can't be right. Okay, so let's try the other option. Let's assume the statement is false. If it's false, then what it says is incorrect. It says that it is false, so if that's incorrect, it must actually be true. So if it's false, it must be true. We are stuck. The sentence seems to be true if and only if it is false. It breaks the fundamental rule of logic, the law of non-contradiction, which says that something cannot be both A and not A at the same time, and in the same way. This is the liar paradox. It's another puzzle that is often attributed to Eubulides of Miletus, the same thinker behind the Sorites Paradox. An ancient version of it, known as the Epimenides Paradox, involves a Cretan who says, "All Cretans are liars." If the statement is true, then the Cretan speaker is a liar, which means his statement must be false. This version isn't a perfect paradox because if the statement is false, it just means that some Cretans tell the truth, which doesn't create a direct contradiction. But the simpler, more direct version, this statement is false, is a perfect, inescapable logical loop. For thousands of years, this was treated as a clever but annoying riddle, a party trick for philosophers. It didn't seem to have any deep implications, but that all changed in the late 19th and early 20th centuries. Mathematicians and logicians were trying to build a perfect, solid foundation for all of mathematics. They wanted to create a formal system where every true statement could be proven and no contradictions could ever arise. And philosophers like Bertrand Russell were working on this problem. Russell discovered his own version of the paradox related to sets. Think of a set that contains all sets that do not contain themselves. Does this set contain itself? If it does, it shouldn't. If it doesn't, it should. It's the same self-referential knot. This showed that the problem wasn't just a quirk of language, it was a deep structural problem in logic itself. The person who truly blew the whole thing open was an Austrian logician named Kurt Gödel. In 1931, Gödel published his incompleteness theorems, which are among the most stunning intellectual achievements of the 20th century. He essentially used the logic of the liar paradox to shatter the dream of a complete and consistent mathematical system. In very simple terms, Gödel created a mathematical statement that could be translated to mean, this statement cannot be proven within this system. He gave the liar paradox a mathematical form. What he showed was that for any sufficiently complex formal system like the one that underpins arithmetic, there will always be statements that are true but cannot be proven using the rules of that system. Furthermore, he showed that no such system could prove its own consistency. And Gödel's work was a bombshell. It proved that mathematics, the very symbol of certainty and proof, had built-in limitations. There will always be mathematical truths that are beyond our ability to prove. The liar paradox went from being a philosophical curiosity to being a tool that revealed a fundamental truth about the limits of human reason and formal systems. It's the reason why we can't create a computer program that can solve every mathematical problem or a perfect system of logic that is free of unprovable truths. The logician Alfred Tarski later proposed a solution to the liar paradox in language. He argued that we need to separate languages into different levels. A statement in a language like English, the object language, can only have its truth or falsity discussed in a higher level language, a meta-language. The sentence, "this statement is false," mixes these levels. It's a statement in English that tries to talk about its own truth value within English. According to Tarski, this is an illegal move that creates the paradox. So, "the snow is white" is a true statement in the object language. To say this, we can say in the meta-language, the sentence, "the snow is white," is true. This separation prevents the self-referential loop. It's a powerful solution, but it means our everyday language is inherently messy and paradoxical. Could our entire universe be a formal system that contains true but unprovable facts about itself? Are there aspects of reality that are fundamentally beyond our logical grasp because of this principle? If a sufficiently advanced AI were to analyze its own code, could it encounter a Gödel-like statement about its own limitations, causing it to crash or enter an infinite loop? What other paradoxes are lurking in our language and logic, waiting to reveal even deeper limits to what we can know? Number 3, when is an object actually moving? Imagine an arrow in flight. It's soaring through the air from the bow to the target. It is clearly in motion. Now let's think about a single instant in time. Just a snapshot, a frozen moment with no duration. At that specific instant, where is the arrow? It's in a particular place in the air, occupying a space exactly equal to its own length. In that instant, it is not moving to where it is, because it's already there. And it is not moving to where it isn't, because it's an instant and there's no time for it to move. So, at any given instant in its flight, the arrow is motionless. It is at rest. But the entire flight of the arrow is just a collection of all these instants. And if the arrow is motionless at every single instant of its flight, how does it ever move from the bow to the target? It seems that motion is impossible. This is the arrow paradox, one of the famous paradoxes of motion proposed by Zeno of Elea in the 5th century BC. Zeno was a member of the Eleatic school of philosophy founded by Parmenides. Parmenides had a radical idea. He believed that all change and motion were illusions. The reality, he argued, was a single, unchanging, eternal oneness. This is obviously a tough sell because we see motion and change everywhere. Zeno's paradoxes were not meant to be just clever brain teasers. They were sophisticated logical arguments designed to defend his teacher's bizarre conclusion. He was trying to show that the common sense view of reality, the idea that things move and change, leads to logical absurdities. If you accept that time is made of instants and space is made of points, Zeno's logic seems to trap you. Aristotle was one of the first to try and dismantle Zeno's argument. He argued that Zeno was making a mistake by treating time and space as if they were composed of a series of indivisible points or instants. An instant, Aristotle said, is not a part of time. It is a limit or a boundary of a period of time, just as a point is the boundary of a line. You can't add up a bunch of points with no length and get a line. Similarly, you can't add up a bunch of instants with no duration and get a period of time. If motion, he argued, doesn't happen in instants, but over periods of time. This was a good argument, but it didn't fully satisfy everyone. The nature of the continuum, of what a line or a period of time is truly made of, remained a puzzle. For over 2,000 years, the paradox remained a major philosophical problem. The real breakthrough came in the 17th century with the independent invention of calculus by Isaac Newton and Gottfried Leibniz. Calculus is essentially the mathematics of continuous change. It gives us a way to deal with the infinitely small. Using the concept of a limit, calculus can describe the properties of a curve at a single point or the instantaneous velocity of a moving object. Instantaneous velocity isn't about what's happening in a zero-duration instant. It's the limit that the average velocity approaches as the time interval gets smaller and smaller, approaching zero. So the arrow at any instant does have a velocity. It's not at rest, it has a property, it's instantaneous velocity. That describes its motion over time. Calculus provided the mathematical tools to describe motion in a way that seemed to dissolve Zeno's problem. It showed how motion could be a sum of an infinite number of states. But has it really been solved? Some physicists and philosophers are not so sure. The paradox re-emerges in a new form in the world of quantum mechanics. There's a phenomenon called the quantum Zeno effect. It was first described by physicist George Sudarshan in 1977. The theory predicts, and experiments have confirmed, that if you continuously and rapidly measure an unstable quantum system, you can prevent it from changing or decaying. It's like the saying, a watched pot never boils, but for quantum particles. By constantly observing the arrow, at each instant you can effectively freeze it in place. This doesn't prove Zeno was right about motion being an illusion in our macroscopic world, but it is a shocking and bizarre echo of his ancient paradox. It shows that the act of observation and the nature of time at the smallest scales are far stranger than we ever imagined. Is space-time continuous, a smooth fabric as calculus assumes, or is it discrete, made of tiny, indivisible pixels of space and chronons of time? If it is discrete, does that mean motion is just an object disappearing at one point and reappearing at the next, like a character in a video game? If motion is just a series of static states, where does the actual experience, the feeling of flow and movement, come from? Could the quantum Zeno effect be scaled up, in theory, to freeze a macroscopic object in place just by observing it? Number 2. Can the fastest ever catch the slowest? Imagine a race between the legendary Greek hero Achilles, the fastest runner of his time, and a humble tortoise. Achilles is a good sport, so he gives the tortoise a head start of, say, 100 meters. The race begins. Achilles is much faster, let's say 10 times faster than the tortoise. In the time it takes for Achilles to run the 100 meters to where the tortoise started, the tortoise has, of course, moved on. Since it moves at 1/10 the speed of Achilles, it has moved 10 meters. So now Achilles must cover that extra 10 meters to catch up. But in the time it takes him to run those 10 meters, the tortoise has moved on again. It has covered another 1 meter. Now Achilles must cover that 1 meter, but in that time, the tortoise has moved 10 centimeters. And so on. Every time Achilles reaches the point where the tortoise has advanced a little bit further. The gap gets smaller and smaller, but it never seems to disappear. The tortoise will always be a tiny bit ahead. It appears that Achilles can never, ever overtake the tortoise. This is Zeno's most famous paradox, Achilles and the tortoise. It's a more dramatic version of the dichotomy paradox we will look at next. Like the arrow paradox, it was designed to show that our common sense understanding of motion leads to a logical contradiction. Our eyes tell us that a fast runner can easily overtake a slow one, but when we break the race down into this series of stages, logic seems to prove it's impossible. Achilles has to complete an infinite number of smaller and smaller tasks to catch the tortoise. And how can anyone complete an infinite number of tasks? Again, Aristotle was the first to offer a serious critique. He argued that Zeno was confusing two types of infinity. There is infinity by addition, like the numbers 1, 2, 3, which go on forever, and infinity by division, like a line segment, which can be divided in half forever. Zeno sets up the race as an infinite series of tasks to be completed one after the other, which sounds like it should take an infinite amount of time. But Aristotle pointed out that the distances and the times involved in each stage are also getting infinitely smaller. Achilles has to cover an infinite number of distances, but he does so in an amount of time that also divides infinitely. So he can complete the infinite series of tasks in a finite amount of time. This was a brilliant insight, but it was still just a conceptual argument. The full mathematical takedown of the paradox had to wait for calculus. Calculus gives us the tools to handle infinite series. The series of distances Achilles has to run is 100 plus 10 plus 1 plus 0, 0.1 plus 0, 0.01 plus 0. The sum converges to a specific number. In this case, it converges to 111.111. Calculus allows us to calculate exactly when and where Achilles will catch the tortoise. The paradox is dissolved by showing that the sum of an infinite number of ever-decreasing terms can be, and in this case is, a finite number. Most mathematicians and physicists today consider the paradox solved by this mathematical explanation. The logic of Zeno was flawed because it assumed that an infinite number of steps must require an infinite amount of time. But our mathematics of infinity shows this is not the case. However, the paradox still feels unsettling. It highlights the strange and counterintuitive nature of infinity. It forces us to rely on abstract mathematics to explain something that feels viscerally simple. The philosopher Bertrand Russell remarked that this paradox, and Zeno's others, afforded grounds for almost all the theories of space and time and infinity which have been constructed from his day to our own. The problem also forces us to question the nature of the physical world. The mathematical solution assumes that space and time are continuous and infinitely divisible. What if they aren't? If space were made of tiny, discrete units, like pixels on a screen, and time ticked by in tiny, discrete steps, then the paradox would dissolve in a different way. There would be no infinite division. Achilles would simply jump from one pixel to the next, and eventually he would land on the same pixel as the tortoise at the same tick of time. Many theories in modern physics, like loop quantum gravity, explore the idea that space-time might be quantized or pixelated at the tiniest possible scale, the Planck length about 1.6 times 10 raised to the power of 35 meters. We don't know if this is true, but it shows that Zeno's ancient puzzle is still pushing at the frontiers of physics. Even if calculus provides a perfect mathematical model, does it truly explain the physical reality of the race? Does it just describe what happens without explaining how an object can physically complete an infinite number of traversals? If spacetime is fundamentally discrete, what does that mean for our understanding of speed and motion? Could an object exist between two pixels of space? And if we live in a digital universe, does that imply that reality is, in some sense, a computation? Number 1, can you ever start a journey? Before you can walk across a room, you must first get to the halfway point. And before you can get to the halfway point, you must first get a quarter of the way there. And before you can get a quarter of the way there, you must get 1/8 of the way there. And before that, 1/16, and so on to get from any point A to any point B, you must first traverse an infinite number of smaller distances. How can you even begin such a task? How can you complete an infinite number of tasks in a finite amount of time? It seems you can't even take the first step. All motion of any kind seems to be impossible. This is the dichotomy paradox. It is the most fundamental of Zeno's paradoxes of motion. While Achilles and the tortoise is about completing a journey, the dichotomy is about even starting one. The name dichotomy comes from the Greek for cutting in two, because the logic of the paradox is based on repeatedly cutting the remaining distance in half. It is Zeno's starkest argument for his teacher, Parmenides' claim that motion is an illusion. It concludes that simply to leave your chair is a logical impossibility. Like the Achilles paradox, the argument hinges on the idea of completing an infinite series of tasks. You must complete task 1 getting 1/2 of the way, then task 2 getting 1/2 of the remaining way, and so on forever. Since there is no first task in this infinite sequence, when you reverse it, there's always another halfway point before any point you name. You can never get started. The modern mathematical refutation is the same as for Achilles and the tortoise. It relies on the concept of a convergent series from calculus, the infinite series of distances 1, 2 plus 1, 4 plus 1, 8 plus 1, 16 plus. The infinite number of subdivisions of the journey add up to the total finite length of the journey. The time it takes to complete each subdivision also gets smaller and smaller, and the infinite series of time intervals adds up to a finite total time. The math works perfectly. It shows that there is no logical contradiction in traversing an infinite number of divisions in a finite time. So, is the paradox just a mathematical misunderstanding? A trick of language based on a faulty intuition about infinity? For most scientists and mathematicians, the answer is yes. Calculus provides a consistent and powerful model for describing motion, and that model works. It allows us to send probes to Mars and build GPS systems. Zeno's paradox is seen as a historical curiosity that spurred the development of more rigorous thinking about infinity and the continuum. But some philosophers argue that the mathematical solution misses the point. The math describes the what, but not the how. It shows that the sums add up correctly, but it doesn't address the metaphysical problem of how a physical object actually performs an infinite number of traversals. The philosopher Max Black, in the 20th century, argued that the paradox reveals a problem not with reality, but with our description of it. The description of completing an infinite series of tasks might be the wrong way to think about what is happening when someone walks across a room. Perhaps motion is a single unified process, and our attempt to break it down into an infinite number of discrete parts is what creates the illusion of a paradox. This paradox, more than any other, forces us to confront the very nature of space and time. Is the space in your room a collection of an infinite number of points, or is it something more fundamental that can't be broken down in that way? Our best physical theories, like general relativity, treat space-time as a smooth, continuous manifold, exactly the kind of structure that calculus is designed to describe. But Theories of quantum gravity, as mentioned before, speculate that this smoothness might break down at the smallest scales. If space itself has the smallest possible unit, then there is no infinite divisibility, and the dichotomy paradox could not even be formulated. A journey across a room would be a finite number of jumps between these fundamental units of space. Zeno of Elea, in trying to prove motion was an illusion, may have accidentally stumbled upon a question that could lead to the next revolution in physics: is our universe analog or digital? If we accept the calculus solution, we accept that we routinely and effortlessly complete an infinite number of tasks every time we move. Does that concept make sense in the physical world or only in the abstract world of mathematics? If reality is fundamentally discrete and pixelated, what are the pixels made of? And what happens in the gaps between them? Is it possible that Zeno was right, and our perception of continuous motion is a powerful illusion generated by our consciousness to make sense of a reality that operates in a completely different and perhaps stranger way?